They spray our skies,
interacts with the magnetic
chemicals.
Space travel is just Mars rover is a complete.
Hi, I'm Rich Lund. This is Debunk Funk. Let's get into it. Why do the seasons change? This is a question with a very well understood answer that you're likely familiar with. As the Earth rotates while orbiting the Sun, at any given time is facing the darkness of space. Half of the Earth is going to be, hence night and day, facing the sunlight, while the other half. But the axis of the Earth's rotation is at an angle, approximately 23.5 degrees. This angle is the direct cause of our seasonal changes. As the Earth orbits the Sun for half of the year, half of that trip, the axis of rotation is going to be more pointed towards the Sun in the northern hemisphere and pointing away from the Sun in the southern hemisphere. This is the half of the year from the first day of spring until the end of summer that the northern hemisphere receives more daylight hours than nighttime. It is the most extreme on the summer solstice, the first day of summer, the day when you receive the most sunlight hours, more sunlight, energy, and also because during this period, this is why during those seasons, the temperature period of time, the northern hemisphere's receiving years tend to be warmer. The opposite is true for the northern hemisphere's winter and fall seasons. It is during this half of the year that along the Earth's orbital path, the axis of rotation is pointed away from the Sun. And if you followed all of that, then you also immediately understand that everything I just said about the northern hemisphere, well, during those same times of the year, the exact opposite would be happening for the southern hemisphere. So on the first day of winter here in Michigan, well, that's going to be Sydney, Australia's first day of summer. With all of that in mind, how does the flat Earth idea try to handle the seasons? How do they try to explain them? In the flat Earth model, it moves around above us in a circle. There's a spotlight sun, circular motion, and if the light, and it's relatively close to the Earth, from it is hitting you, then that's day, and if the light doesn't reach you, then that's night. Already, when first examining this idea, plenty of questions naturally arise. What is the sun? What material is it? What's responsible for its energy output? Why does it float above us and not fall down to the Earth? What's causing its circular motion? Finding no real consensus to any of the answers to those questions from the flat Earth perspective, I can only assume they're still working on it. For now, let's just give them that's how their sun works. In order to use that sun to explain their seasons, they claim that the circular changes, and that's the cause of the different diameter of the sun's path above our different seasons. On the first of our heads, well, the diameter change of northern hemisphere's summer, according to their model, this would be the day when the diameter of the sun's path is the smallest, and the territory north of the equator receives the most amount of energy from the sun. This would be the northern hemisphere's first day of summer, summer solstice. From that day forward, the diameter of the circular path increases. The circular path is spiraling out a little bit each day, and the northern hemisphere is receiving less and less and less sunlight from that day forward. This continues until the flat Earth sun's circular path reaches a maximum of a diameter, and this would be the day when the northern hemisphere receives from that day forward the flat minimum amount of sunlight. The Earth's sun then begins to the first day of winter, and spiral inward again, and the cycle continues. In short, the flat Earth model's explanation for the seasons would say that the longer daylight hours and warmer temperatures of the spring and summer seasons for the northern hemisphere are because the sun's circular path is a tighter circle above our heads. And the colder and shorter days of fall and winter, that's when the sun's circular path is further away from us. Alright, are you up to speed? So we've done a quick crash course on the two different models and how they explain the seasons. Pin both of those ideas for a second. What makes a model a good one? A successful one? In the science classes that I teach, I bring up three major criteria that makes a model or theory a good one. Second, the model is as one. Number one, the model is simple as it can be. Nothing must fit the evidence. Nothing is extra that doesn't need to be there. And third, the model can make accurate predictions. In fitting the evidence, this would mean that the model, in its attempt to explain some phenomenon, is never in conflict with something that is readily observed. Already, the flat Earth model's explanation for the seasons has a fatal problem here. In trying to explain the seasonal changes due to the sun's circular path having a different diameter, I can at least see how the northern hemisphere's longer daylight hours and warmer temperatures could sort of be explained. But when it comes to the southern hemisphere, the flat Earth model's explanation for the seasons falls apart immediately. If the flat Earth model were correct, and Australia is larger, that does nothing to explain summer is due to the sun being why Australia's first day of summer with circular path's diameter being large to have as much sunlight as it does. If we look at a flat Earth azimuthal map, here's an image that shows where sunlight would be hitting on the northern hemisphere's first day of summer at some time during the day. Nothing looks terribly in conflict with their idea. But in the southern hemisphere, on their first day of summer, here's what the flat Earth sun would have to be doing according to their azimuthal map. And somehow the spotlight is able to reach its light in all the places that are yellow, yet all the places that are not cannot see the sun. Do you see any issue with that? How can those who are here and here and here be able to see the sun, but those who are closer to it, counting this further, no matter the season here, here, and here, not season, a day is still 24 hours to be able to see the sun. Compowers. So if the flat Earth sun's circular path has the largest diameter around December 21st, it must travel that circular path faster than 6 months later when the path is the shortest. And in the southern hemisphere, somewhere like Australia, this would be blatantly noticeable. The apparent speed, though, of the sun across the sky is the same, no matter where it's observed over the globe. 0.25 degrees per minute, or if you prefer, 15 degrees per hour. From the get-go, already the flat Earth model is in conflict in multiple ways with things that can be readily observed. But let's now shift and look at the third criteria of a good model. Can do the first two criteria, the ability to make accurate predictions. Fit the evidence, and it's as simple as if a model, any model, it needs to be, it still doesn't really amount to much if it can't fit the third criteria. How strong a model or theory is really judged by how powerful it is at making accurate predictions. That's why we try to come up with models and theories in the first place. There's power in being able to predict. Whether Flat Earth likes it or not, their model for explaining the seasons, it makes a prediction, and one that we can test out in our own backyards. Here's what it predicts. If the Flat Earth model's explanation for the seasons is correct, then from the perspective of here in Michigan, on summer solstice at solar noon, that is when the Flat Earth sun is going to be the closest it's going to be to this observer. Compared to noon, that sun should be significant any other time during the year, and significantly further away. And then on the first day of winter at solar, usually we should be able to observe an apparent size difference of the sun. That is what the Flat Earth model predicts. Now, according to the globe model, the sun is much larger than the Earth. It's 93 million miles away. And on the first day of winter or summer, or really any day of the year, anywhere on the globe, if you can measure the sun's visual apparent size, it will be no different on any other day. While there would be extremely slight differences, visually none significant enough to notice. Now, obviously, if somebody wanted to test this out, this experiment would take a minimum of 6 months. But if you're patient and curious, it can be done. In Debunk the Funk number 2, I made a tool that anybody could duplicate this, but the general idea is that it's for a pretty low cost. Check out that it's an affordable solar filter, which you need in that episode for full details on how to duplicate in order to see something's edge. The screen is there, so we have a grid we can use to measure with, and the white out dot in the center just ensures that we're always using the same part of that grid. So, on Friday, June 21st, 2019, Michigan's first day of summer, and then more recently, on Saturday, December 21st, Michigan's first day of winter, I used this tool to test out our experiment. And just as a note, you'll see, as before in Debunk the Funk number 2, I set the camera to the same focal length, to the same focus. Here we go. Alright. It is June 21st, 2019, the first day of summer. At solar noon, the sun solstice. According to the flat, should be as close to me, Earth idea, today as possible. Solar noon occurs at 1:40 p.m., so that's when we're going to conduct our experiment. Or thereabouts, depends on if a cloud's in the way or not. We're going to take a measurement as to the visual diameter of the sun.
Okay, just as before, in Debunk the Funk number 2, I'm going to turn the camera so that way it is all the way focused, zoomed out, same focal length in as in Debunk the Funk number 2. Turn the camera on now. And then I'm going to point it at the sun. There it is. Just a little bit there. Get it on the right hand side of the screen. Okay. Now we take the measurement. It's tough to see with all this sunlight if I'm getting this. Oh, there it is. Now I gotta find my whiteout dot. There it is. Get it in the center as best I can. There we go. Measurement has been taken. Now the next time you'll see me will be on the first day of winter. I gotta wait 6 months. You just have to wait a couple of seconds. See you then.
And here we are, first day of winter. And I gotta admit, like, in Michigan, this does not happen too often. We've got a totally cloudless sky. December 21st, 2019. And there's our sun. We're getting close to almost time to do it. Solar noon.
Solar noon today is 12:35 p.m. in my location. We're at about 12:34 right now. So I'm going to turn the camera on. Just as before, going to the full focal length. So we are fully in the same position as we were first day of summer. And for Debunk the Funk number 2, find the sun. Hit record, and then point it towards the sun, get it on the right hand side of the screen, and now with our instrument, let's take the measurement. Where exactly that was at. Focus in more again. Alright. There, I'm seeing the sun on my screen. There's the sun now. Okay, solar noon on the first day of winter. December 21st, 2019. We have our measurement.
And just
Alright.
so we're clear,
Let's analyze the data.
this was happening now that we're done, 12:36, so yep, we hit that right at solar noon. Alright, let's look at the results. On the left, here's the sun at solar noon on the first day of summer here in Michigan, summer solstice. And on the right, from the same location in Michigan, here's the sun at solar noon on the first day of winter, winter solstice. The visual diameter of the sun is unchanged. If the flat Earth model was correct, then it predicts that the visual difference of these two images should be significantly different. The sun is definitely much closer in one than the other according to their... Now, while we're at it, because we model, yet there is no... They use the same camera with the same focal visual difference in size. Length and the same measuring tool as we did in Debunk the Funk number 2, we can compare those images to these new ones. These are all in Michigan as well. On the far left, this is the sun right after sunrise. In the middle, that's at solar noon. And on the right, that is the sun right before sunset. The apparent visual size of the sun is no different. The important question to ask now is, of the two models, which model predicts these results and which model is in conflict with them? I'm Rich Lund. Thanks for hearing me out. And remember, the world needs critical thinkers. Make sure you're one of them. Catch you next time.